Take two. I'm Beth Baranski, I'm the moderator, and this morning we're going to be talking about Karst databases, and we've all gathered here to the things that we're talking about, like land use issues, fish and wildlife habitat, water quality, are all literally underlain by the karst terrain of the Driftless Area. The dissolution of our carbonate bedrock produces features like sinkholes, caves, enlarged crevices, abundant springs. And scientists from Illinois, Iowa, Wisconsin, and Minnesota are here with us this morning to talk about the data that they're collecting on these karst features, about how they're storing and managing that data, and who has access to it. We're going to start off with Illinois, with Sam Panno and Don Keefer. Sam Panno holds Bachelor of Science degrees in Biology and Geology, a Master of Science degree in Geology, and has done postgraduate work in hydrogeology and groundwater chemistry. He is a senior geochemist and has been with the Illinois State Geological Survey, part of the Prairie Research Institute of the University of Illinois, since 1988. Currently, Sam is leading research on the geology, hydrogeology, and groundwater quality of karst regions of Illinois, the location, significance, and origins of saline springs throughout the Illinois Basin, the origin and evolution of Illinois Basin brines, and the use of speleothems in identifying paleo-earthquakes in the Midwest. Don Keefer is a senior hydrogeologist, the head of the Hydrogeology and Geophysics section, and the founder and head of the Earth Systems Visualization Lab at the Illinois State Geological Survey. He has a Bachelor of Science in Geology, a Master of Science in Agronomy, and is currently working on a PhD in Informatics, all from the University of Illinois at Urbana-Champaign. His research interests include the use of statistical methods and visualization tools for characterizing and modeling multi-scale problems in hydrogeology. Sam and Don.
Thank you. This morning, Don Keefer and I are going to talk in tandem. So Don's going to go through the last 3 or 4 slides. Sorry. The other co-author on our paper, our presentation, is Don Lumen, who has a PhD in geography at the Illinois State Geological Survey, and is responsible for the LIDAR elevation models produced there. So what I'm going to do is talk about a little bit about what we're doing in Illinois, how we're getting the data from all of this research into publications and making it available to the public. We don't have a database per se, an official database for karst at the State Geological Survey, and that's something that we're starting to look at. So this is Illinois karst in green, I guess, and this is USGS karst map showing the karst areas surrounding Illinois. We have about 25% of the state that has karst features and karstified carbonate rock. So that was a map we produced in the mid-90s. This is southwestern Illinois. What we've been doing is mapping sinkholes, cover collapse sinkholes throughout the state. And this is the Illinois sinkhole plain. And essentially, the entire area is being eroded slowly, and the soil is going down into these sinkholes. The surface area is about the sediment is about 30 feet thick, and it's getting thinner and thinner. So very dense karst. We're also mapping crevices in road cuts, outcrops, and in quarries all over the state, particularly in southwestern Illinois and in northwestern Illinois, in Joe Davis County and the surrounding counties. We're also collecting water samples from springs and wells. These are a couple of cave springs in southwestern Illinois. And we're looking at chemistry, isotope geochemistry, microbes, pesticides, and recently pharmaceuticals and hormones, which are indicators of human contaminants, human-related contaminants, for example, from septic effluent. In addition, we've looked at sediments within the caves to look at climate change and the origin of the caves. This is a passage, a side passage that was filled with sediments in about 40,000 years ago, and so there was a major event between 40,000 and 25,000 years ago that resulted in filling some of these passages. Possibly the entire cave we're in this photograph, which is 16 miles long. The sediments were cleaned out of the main passage, leaving these side passages filled with sediments, so we could date, burrow into them, and figure out when the sediments came into the cave. And then we also looked at stable isotopes to look at climate change. We worked with the State Museum when we were in the caves, and this is in southwestern Illinois. It's Focal Pole Cave, very large cave, and we noticed a lot of bones in one area. This is, I believe that's a sloth femur, a femur from a giant sloth that we found, and then there were maybe 20 other bones that we collected, and they're studying them to look at megafauna in Illinois during Pleistocene. And another thing we look at is these stalagmites. They're white, and they're fairly, you can see this one, it's kind of like icing on a brown stalagmite. And what we found was earthquakes associated with the New Madrid seismic zone generated these things. So we dated maybe 10 of them, and they all date back to about 200 years before present, about 1811, 1812, when the New Madrid seismic zone had about 3 or 4 major earthquakes, magnitude 8. So very, very huge earthquakes. And earthquakes, paleo earthquakes, prehistoric earthquakes, are also recorded in these stalagmites. So we're finding this in Indiana, Illinois, and Missouri as well, and we're doing some work on that. So how do we get this information out without a database? Well, what we do is we publish at the survey with circulars, internal publications, and within them we have the ability to include large databases, all of the data going into this research. And then this is currently we're mapping historic sinkholes and other karst features using historic aerial photos. This is from 2005, and in southwestern Illinois, you can see the sinkholes. And then in 1940, during the Dust Bowl period, it was so dry that the outer rims of the sinkholes had very very dry white cast to them, so it brings out the sinkholes. So by using these, we were able to map most of the sinkholes down in southwestern Illinois. And what we found, initially we looked at USGS topographic maps, and went along and said, okay, sinkholes, and drew lines around it. And then we used the aerial photos, and that showed us about 30% more sinkholes than we had before. Which in this case, this slide, going from I think yellow to red. The red are the ones we found with the aerial photographs. And then these are a couple of quadrangle maps from that area showing all of the sinkholes. So you can see there's probably 15,000 sinkholes just in these two quadrangles. So it's a lot. More recently, we're using LiDAR elevation models and looking at the same areas we looked at Joe Davis County as well. And we've been putting these sinkholes into a geodatabase, which is here in ArcGIS. So the data, each one of these sinkholes has a unique identifier and attributes of shape, length, depth, and so on. And so we're taking those data and publishing maps and reports, and the data are available online, sort of. You know, we checked before I left for the meeting, and they're available, but only to people at the ISGS. So we're looking at that to make this more available to the public. But you know, all of the data are within these maps and in electronic versions. And you get the map paper version, but that's the state of our database, our geodatabase at this point. And then Don's going to talk more about that. So, thank you.
You didn't do these.
Oh.
Fine. We should do the
Yeah. Okay. All right. Okay, so I was talking about LiDAR. We went from aerial photos to LiDAR. And with that, we could see an additional 20% more sinkholes. And in southwestern Illinois, we had a flight over the sinkhole plain, and we had the Don Lumen set up the flight, and he had this area flown so that instead of having maybe one laser point per square meter, it was more like 8 laser points, which gave us a lot of data. So you can see details in these sinkholes, slump features that we've never seen before, and these are under trees, so we rarely see any of that. And then in Joe Davis County, we looked at karst features, particularly in this case crop lines, which I'll show in a minute, and mining areas and sinkholes. So what I'm going to do is look at this small area too in the southwest, and you can see sinkholes in the cover collapse sinkholes in the sediments. We're looking at lineaments created by these, so we could compare them to the crop lines. And essentially, the sinkholes follow crevices. And so these are the crop lines, and we digitized 18,000 of these lines. And basically, these lines are cover crops, alfalfa, that is growing in about 2 feet of soil. So the alfalfa roots go very deep, and they go into the crevices and fractures. And and only, and this was during the drought of 2012, so only the alfalfa overlying the crevices actually greened up. Everything else died. So we digitized these, and those data are in an ArcGIS geodatabase. And then this is part of what the database looks like, with the attributes of the crevices and the orientations of the crevices. If you look, most of them are east-west in orientation, with a subgroup that says north-south, which has to do with plate tectonics and fracturing of the continental rocks. And then this is what the database looks like within the map for just these blue ones. So it's accessible, it's permanent, but not in a formal geodatabase yet. Okay, Tom.
Sorry.
Sure.
So again, Sam asked me just to touch base a little bit on more formally where we are with the data structure. These, as he pointed out, were a couple of county-level projects that he worked on over a period of about 20 years or so. And so the data structures themselves kind of grew organically. It wasn't, they were going to go out and do this. In Monroe County, they've got, like he said, they've got quite a bit different data set than they do up in Joe Davis County in the Driftless area. Currently, most of the information is in these ArcGIS, what they're called file geodatabases, which is, in my way of thinking at least, a kind of convenient structure that allows us to put a bunch of different kind of spatially referenced data sets into. And it, currently though, we're looking at information that's primarily related to the cartographic features that they were putting into the maps. As Sam pointed out, there's some circulars that he has on water quality. There's other data layers, some of the polygons from the topo lines that aren't in the geodatabase. What we're talking about doing in light of not just this symposium, but in a larger context, is trying to maybe generate a single file geodatabase that would be kind of a compilation of all information. And that way, what will happen is that it has a little bit easier, it's a little bit easier to track a single data set that might be a little bit larger than a couple of project ones. It allows us to establish kind of a consistent, overarching set of files and fields, but recognizing that we're probably not going to go back in Joe Davis right away and add the fields that were in Monroe and probably vice versa. But at the same time, it'll help us identify programmatic priorities. And one of the things that I've kind of done here, and I just put it on one slide to kind of keep it a little bit simple. But we're really talking about the Karst areas map that he has done in, was it 96 with Pius Weibel, adding that into the single features database. So really it's like a one-stop shop for the information we have at the ISGS on Karst information. At this point, these are the things that are in the different types of products of Monroe County. The sinkhole, swallow hole, centroids, and you notice those little points that he had. Those are an attempt to get at the centroids. One of the things that we may explore, and I put it in here just as a matter of argument, maybe if nothing else, but one of the things that gets lost is how did you collect that data? What's its accuracy, the kind of the pedigree of that information, because that just helps you understand, again, the reliability maybe of it. Moreover, there are a couple different methods may give you the same type of information, point information, but one might be more accurate than another. And so if we can have what I'm calling here just the source method of how these were generated, that might really help. And these would be the swallow hole boundaries, and he had that in Monroe County more. Delineations, as he showed, whether they be from digitized from the field work or digitized from imagery, the resulting, even the potential to store the resulting images associated with this. This is a hill shaded relief again with some contours that have been generated. The goal is to really put, again, everything into one kind of package. Now we can talk a little bit later on the value of standardization or not. My suggestion is that we not even worry at our place about standardizing internally to the ISGS. In other words, again, not go back for Joe Davis and try and create all the points in data that were in Monroe. He spent a lot more time down there than up there. The degree of karstification down in Monroe is, as you noted, extreme relative to geodata's. It wouldn't be hard, though, at the same time to go back and add those over time. So it gives us that flexibility. I'm a real advocate for putting in things like the actual elevation models and the imagery, the aerial photography, and publication information associated with these actual efforts and publications that we came out with, because it's very likely, and it's hard to believe right now given the cost of LiDAR, but it's very likely that we'll be doing LiDAR over time, multiple times. And so, you know, as you saw from the aerial photography, if you went pre-40s, in the 30s, 1930s, you saw a lot of sinkholes. But then with changes in agricultural implementation and the needs to maybe maximize our farming acreage, we've filled in a lot of those sinkholes. They're not as obvious. That same kind of time series change is going to be evident in the LiDAR as well. And so actually copying, and some people get a little bit uncomfortable for talking about data sets because you've actually got the same information more than once. But what it does is it creates a really good, strong, reliable data set that in 30 years, maybe we go back and we actually see the actual data that Sam used in these. And then we can compare it to the data sets that are on file. And it gives us a little bit more of a before and after insurability. Plus, we can tag it with, well, which were the actual publications that one, because he's got quite a bit of journal articles that he's published, he and Don and others, as well as the circulars you saw. And then again, a little bit of metadata. Which is basically, for those of you not familiar with databases, metadata is just documentation. It's an easy way to think of it. So what is not captured in the data that might be really helpful to understand the relevance or accuracy or reliability of the data. So that's kind of our goal. So that will, that's about all I have for now. So, thanks.
Now we're going to hear from Iowa. Bob Libra has degrees in geology from the University of Wisconsin at Superior and Indiana University. He's worked with the Iowa Geological and Water Survey since 1982. His work at the survey has involved a wide range of geologic, hydrologic, land use, and water quality investigations. In addition, he says he has dabbled in the wonders of karst for many years. In 1999, he became supervisor of the survey's groundwater and stratigraphic studies group. And in 2003, he was appointed State Geologist of Iowa.
Thank you, Ben. So yeah, we'll talk a little bit about what we've been doing mapping karst features in Iowa, those annoying holes out in the cornfields. Calvin Walter is a very talented GIS analyst with DNR. He's responsible for a lot of the mapping that has been going on it, so I wanted to give credit where credit was due on that. The efforts we've had in Iowa to map, locate, database karst features have mainly been regional efforts, and it's mainly focused on sinkholes. So we have not tried in any large-scale sense to map springs or losing stream reaches, things like that. We have done that on some project-level work, such as the Upper Iowa watershed or the Big Spring groundwater basin, where we more holistically mapped a lot of karst features out. But for the state, it's mainly been just trying to get sinkholes themselves located. And this work started in the late 70s, early 1980s, by taking for the northeast part of the state, the Driftless Area and some areas adjoining it, and manually transferring all the sinkholes noted on county soil surveys and just compiling them together onto a map. So it was a very large effort, and it employed a lot of students for a long time. And that's really what we had for quite a while until somewhere in the 90s, the digital soil surveys came along, and you could extract that point information and really do it across the state. The current efforts, the state obtained LiDAR in about 2008, and DNR also had a project to go back and georeference historical air photography, a complete set of the state for each decade since the beginning of the 1930s. So you've got this 10-year tracking of what aerial photography was showing, plus LiDAR saying what's on the ground now, or at least as of about 2008. So you get the LiDAR views where you can see things that the soil survey didn't go to look at. They didn't spend as much time tromping around in the forest as they did in the agricultural fields. And that's where a very high density of sinkholes is, and sometimes that's why it's still forested, because nobody's gone in to try to farm it. It's too many holes in the ground. Versus the views from historic air photography, saying what was on the ground in the 1930s. And that those old views are important. Depending on what you're trying to do, what you're trying to assess, you might want to know what's there now. Is there an open hole out there that liquid can run into and directly access the underlying bedrock aquifer? If those sinkholes are plugged, that doesn't exist anymore, but the conditions that created the karst are there. And so that's also important to know. There's kind of two different aspects to it. If you look at the Bedrock Geologic Map of the state and kind of focus in on that northeast corner, we have a couple called 3 limestone units that are the main karst formers. You've got the Galena limestone, you've got Silurian rocks, and Devonian rocks also. Those are a little further to the west. If we looked at what we had from that original compilation of the soil surveys, the sinkhole distribution would have looked like this. And the big belt running in the far northeast corner of the state is on the Galena outcrop, and the belts running kind of northwest to southeast, and then parallel along the river is mainly in Silurian rocks. And the Silurian is a lot more likely to show karst features where you're near its zero edge, what we call the Silurian escarpment. When you back off from the escarpment, you see a lot less sinkhole development. And you're also, in a way, though, getting out of what you would call the driftless area. You're getting into an area with thicker glacial till cover, and so even if the rock has the features, the solutional characteristics to allow collapse and karst activity, you're not seeing it because it's buried deep enough. If we take a look at what we have now after looking at those counties with LiDAR and with the historic photography or current photography, you see pretty much the same pattern, just an awful lot greater density in those areas. You do see some increase in the number of sinkholes kind of in the outlying areas, but mainly you just get an increase in the density in the areas where you pretty much knew most of the karst action was already going on. And if you look at where sinkholes used to be and that have apparently been plugged either by Mother Nature or probably by the landowners, they follow pretty much the same pattern, really the same patterns going on there. So if you look back in one of these views from 1930, you see roughly a section of land, and it's got an awful lot of sinkholes, and probably 30 or 40. They were still there in the 1950s, but you look at 2010, and the little dots on there are where they had been mapped, and most of them have been completely filled in, and you really don't see much of a trace of any karst activity around there. And yet the conditions are the same now as they were in 1950 when the place was pockmarked with them. And a current LiDAR, an ocean view doesn't really show you too much either. You might get suspicious when you look at some of those crinkles there and you know what used to be there, but frankly you're not really seeing anything. So if you take it by the numbers, the old soil survey for that belt of 7 or 8 counties gave us about 8,600 sinkholes. The LiDAR suggests about 28,000 currently out there, and somewhere around 10,000 appear on something in the past, but we don't see them today. So that's a lot of filled-in holes in the ground out there. We have a few other places in the state where there are concentrations of sinkholes. Just to the west of the driftless area, there is a belt on the Devonian age rocks, which have an awful lot of karst activity in them. there you get some of one of the problems with internal consistency in databases. That nice straight line edge. Well, you had people who, when doing the soil survey, were looking for sinkholes, and you've got other people who didn't. And on the right, they would refer to things as closed depressions, crossable, or they would refer to them as a sinkhole, crossable by farm equipment. Okay? And in the counties to the west, they just called it closed depression. And so there's always kind of been this, just because the state code, when it comes to certain kind of regulations, it says you can't do this, that, or the other within X number of feet of a known sinkhole. Well, what's a known sinkhole? Is it something that the soil survey called a sinkhole, or is it the same thing, but they just called it a closed depression? So that's one of the problems you run into. There's karst scattered around in the southeast part of the state on Mississippian rocks, and even in the central part of the state, where underneath the most recent glacial advance, the Des Moines lobe, so it was under ice only 14,000 years ago, there's a few places where rock is shallow. There are quarries. There are Mississippian limestones near the surface. There are sinkholes. There are losing streams. And if you plop water wells down into those rocks, you'll produce 1,000 gallons a minute with about 3 feet of head loss when you're pumping it. So there's buried karst out there, but there's very little signal of it on the landscape because it's down more than 100 feet of basically clay matrix glacial till. In terms of how we hold this data, it's all part of the DNR's GIS library. So it's put in with the same kind of database standards, the same stuff the Illinois guys were talking about, National Geographic Data System standards, whatever they call them, metadata to describe how the information was collected, and some guess as to its accuracy, things like that. What we've used it for is with a variety of online mapping tools. Okay, so if you're building, for an example, an animal feeding operation, you have certain regulations to meet if you are in a karst area, and you don't have to meet those if you're not in a karst area. So how do you map that? That could be a good discussion around the campfire over cold ones. What we have done is taken the locations of those sinkholes and put a 1 mile buffer around them. So if you're 1 mile from a place where a sinkhole is or has been, then you're in a karst area, and those regulations clearly apply to you. If you're out away from where all the colors are, you're in areas where you may be underlain by carbonate bedrock, but it's buried by at least 50 feet of quaternary cover, and we don't see much karst solutional collapse kinds of activities going into it. In between, the kind of pinkish colors are areas where you may be more than a mile from a sinkhole, but you're on shallow carbonate rock. And those are areas where if you're going to build a certain kind of facility, you may have to do a little more work to see whether you have to meet these regulations or not. And that I think is really this kind of application where if you're looking at building this, or you've got a guy working for you, helping you go through the rules, you can get online and you can see this and see what your situation is. So we'll stop there. It's important to know where sinkholes are, especially the ones you can't see. This is an example of a brand newly constructed sewage lagoon back in the 1980s in the little town of Garnavillo, Iowa, where there are no sinkholes visible at the surface. It's an area with a little bit of a thicker quaternary cover, but right over the Galena limestone. And so they cut some nice lagoons into the hillside, let some stormwater build up in one. There was a couple feet of water in it on Friday afternoon, and it was gone Monday morning. All through one little hole, because they cut it within 4 feet of the top of the Galena limestone, which you can just see the color of a little bit in the bottom of the hole there. So that's the Iowa story on it, and we'll pass the baton along.
master's degree in geography from the University of Wisconsin-Milwaukee and GIS certificates from the Universities of Wisconsin in Madison and Milwaukee. He is a geographic information specialist and has worked at the University of Wisconsin Extension's Geological Survey since 2010. He's involved with quaternary, bedrock, and hydrogeologic mapping and modeling, including the construction, analysis, conversion, and integration of spatial data into projects.
Thanks, Beth. Like she said, my name is Steve Mauel. I'm a GIS specialist at the Wisconsin Geological Survey. I'm going to talk about karst features and karst feature detection and database construction for Wisconsin. Our karst happens on both sides of the Wisconsin Arch here in areas where there's limestone. The difference is, over here was glaciated repeatedly, and over the Driftless Area, obviously not. So we kind of have two different forms. Over in the eastern part of the state, it's like glacial karst, where you can see this is from Door County, and the bedrock has been scoured over and over again. Very little cover on the top of the rock, extensively fractured, and any previous karst features have been obliterated, at least on the surface. Same thing a little further south, down in Calumet County, rock immediately beneath the surface. You can see it in the LiDAR contours. You can also see the roads and the fence lines where people have piled up rocks, things like that. Over in the western part of the state, you get a little more classic karst features. This is Cave of the Mountains down in southwestern Dane County. This is Eagle Cave over in Richland County. And I really like this photo of a quarry up in Vernon County. A lot of classic karst features: dissolution in the quarry wall, bedding plane fracture, where water is seeping through kind of planarly, and extensively fractured also. So in the past, this is how we've reported or had karst features reported to us. It was an intra-agency form. The only people who were reporting these features to us were NRCS, DNR, USGS, someone who was kind of with another agency. I have a stack of these in my office about this big, maybe. There's some good information on there, but not digital per se as yet. Our new website went live 6 months ago. And right up here, you click on this button and it brings up karst and sinkholes. You click on karst and sinkholes, it brings up the karst and sinkholes webpage. And down here in the corner is a report a karst feature. And it takes you to this form. So now it's totally open to the public. It's almost anonymous. You don't need to put your name in there, but you do need an email. You can upload pictures, descriptions, GPS locations. We're hoping for a little more public participation. It's been 6 months. We've only got 6 reports. So people need to step it up a little. As far as research goes on karst, in 2007, a group of people got together and wrote the final report for the Northeast Wisconsin Task Force. I think at the time they thought it was, they would agree that it was a fairly benign document. It wasn't. It was controversial. It brought up a lot of issues about land use and karst features, and defining karst features and buffering those features for whatever use. I think a couple years ago, we put out the karst fact sheet because there were so many questions about it. And it's kind of been an iterative process. We've always had little karst pamphlets and information on karst. But this is more of a how it's happening, where, and why for the general public. And there's this publication, the Assessing Ecological Status of Vulnerability of Springs in Wisconsin, by Sue Swanson, who is in the audience. And included with this publication is a very large springs database. We all know without water, there's not going to be any karst. The two are intertwined. So, from my perspective as a GIS specialist, in order to map these and catalog these and identify areas where maybe they need to be confirmed, I'm looking for a couple different things here. Number one, high resolution bedrock elevation and geologic mapping if it's already been done. That includes all the subsurface data we can get our hands on. all the water well records put on the houses and the barns and the factories, and getting that three-dimensional picture of what's underneath the ground. I split these up. In the eastern part that's been glaciated, I refer to as closed depression mapping. They're much more subtle features, they're much more broad. Some of them have a drain to that feature. Over in the driftless area, I call it sinkhole detection. It's a finer, more pointed, smaller drainage area. In the eastern part that's been glaciated, the drainage pattern is very immature, it's rolling topography. In the western part, it's very mature. It's dendritic branch pattern and lots of tree cover over areas that are unfarmable. It's difficult to find sinkholes. So these last two obviously dependent on LiDAR data and the availability of LiDAR data. All of these are time consuming, some of them more expensive than others. As far as the high resolution bedrock elevation mapping in Wisconsin, this is kind of a little progress map I put together. Some of these have been completed. But as you can see, there's a number of them in the driftless area that are under construction right now. It's a lot of work, a lot of student hours, it's a lot of point dragging. It's time consuming. And this is a progress map released by DNR in August of the LiDAR availability for the state. And you can see they're getting close. 2015, there'll be just about all the driftless area in Wisconsin will have LiDAR imagery available to the public. So these kind of automated processes where you can find targets to go verify or include or exclude from your data set via air photos or whatever method can take place in these counties. And if I get the information out there, I don't have to be the one to do it. Other people can do this. So I'll give you some examples of closed depression mapping and the kind of techniques that we've employed in the past to catalog these features. This is Calumet County, Wisconsin, in the glaciated part, rolling topography. 2-foot contours from LiDAR. And these are the sinks, these blue features. And these are the drains to those sinks. Now the problem with this is that the LiDAR elevation takes data from all of these roads and driveways. And it sees that as an impediment to water flow over the surface. In order to change that, I need to get rid of the roads from the elevation data. Because at every one of these little driveways and road intersections, they've put a drainage culvert in there to allow the flow of water underneath these roads. So I need to allow that flow of water. So what I do is I turn everything into points, and I take every point within a certain distance of the road center line, and I delete it. So here's the old delineation of closed depressions, and here is it without roads. And it changes things drastically. So I employed this in Calumet County, and I gave it to the county, and they went out, and I drove around with a laptop and verified a lot of these. It's pretty accurate. So this is Door County, Wisconsin. I ran a similar model and conferred with the Landing County guys up there to say, you know, what fill level was appropriate, what resolution for the DEM was appropriate, and they thought that this gave us the best results. So this area outlined in blue right here, and goes actually off the page, all drains to a little blue dot right there. I'll zoom in on that place, and it's called the C and M sinkhole. And they've even ditched to go to that sinkhole. And there it is. That entire area drains to a sinkhole that then goes underground and travels over half a mile to somewhere else and exits. Here's another area in Door County. This entire area outlined in blue all drains to a tiny little dot right there. I'll zoom in on that. And they've even put a pond here to let things settle out. Maybe P, N, and K. A lot of agriculture there. It all flows underground right there. It comes out, I'm not sure how far this went, a third of a mile away. So a little bit different in the western side of the state, obviously. Like I said, much more mature drainage pattern. the size and shape of these features are very different. This is in Crawford County. I did a lot of my master's research out here, so I had kind of a head start as far as the general geology of the area. LIDAR hill shape, that is the Sinope group on the top of the ridges, and that's the Prairie du Chien. And right here is the Prairie du Chien-Jordan contact. Now what I'm missing in between the Prairie du Chien and the Sinope is the St. Peter. It doesn't present itself at land surface. It's an easily erodible, kind of varied, cemented sandstone that doesn't outcrop. So that's going to have to be extracted from well records for me to get that layer in between there. But I'll zoom in on this little area right over here. And they're tiny little sinkholes, and I can't really tell if you can tell, but there's little pink dots in some of these. So it got that one, it got that one, it got that one, it got that one, but is that a sinkhole? Did it miss that? What about this? And this is under tree cover right here. And it still identifies, you know, anthropomorphic features. And I haven't extracted the roads from this yet, so. There's the Sinope group, and those are the areas which drain to those little sinkholes, or those drains. So again, these driveways, these roads need to be removed from this in order to get a more accurate picture of how these sinkholes, where these sinkholes are, and which ones need to be verified. So as far as database construction, we have loosely organized databases per county, and it would be very easy for us to funnel this into some kind of data structure that already exists. I don't need to go, and I know Calvin's done a lot of work on this about how you organize this data and how you capture this data and go out and verify it. I don't need to go put a whole lot of thought into it. There's a lot of publications on this already. It would be very easy for us to just load our data into an existing database schema. The real problem is funding. Our funding continually goes down, and we have to go out and get grants to perform our work, which means we don't really have a say. We have to perform the work that we've given the proposal to do. So that would involve us requiring a grant to perform a Karst study, to develop a Karst database. So that's the state of Karst feature identification and feature storage in Wisconsin. We're kind of at a standstill. So, sure.
Last, we're going to go to Minnesota, and Bob Tipping. Bob has a degree in history from Carleton College and a master's in geology and PhD in water resources science from the University of Minnesota. He is a senior scientist and geologist who has worked full-time at the Minnesota Geological Survey since 1990. He describes his job as a combination of research and outreach. His research interests include the geology, hydrogeology of fractured and karst terrain, groundwater surface water interaction, aquifer characterization, groundwater chemistry, and GIS applications to geologic, hydrogeologic research. His outreach tasks include teaching, serving on technical advisory boards, and responding to public inquiries about anything Minnesota groundwater related.
Okay, thanks, Beth. Okay, I don't have pictures for you this morning, but I'm going to try and mention some of the ones that you've seen so far relative to what we're doing in Minnesota, and try to go through this in sort of an orderly fashion. Calvin, if I miss something, please speak up. So Karst Features Database is what we're talking about. And in Minnesota, this has been going on for quite a while. And I think Calvin may have covered some of the history of that yesterday. So I'm not going to go into that, except to say that the data is currently stored in GIS. It has mostly point features, is what we've been talking about most of today. So these would be items like sinkholes and springs primarily, but it also includes stream sinks. But mostly sinkholes and springs. So in other words, the stuff that you can see at the land surface. And this has really been the focus of Karst databases up until about this point, largely. So let's talk about that for a second. So you're talking about sinkholes on the ground, and you can see, you can map. And as Bob has pointed out, and Sam, and the work that's being done in Wisconsin, is that these features are many times ephemeral features. So they're here for a time, they get filled in, they disappear. So the key issues that we've been dealing with in mapping these things and putting them in the database is really focused on how was that sinkhole located? Was it done by LiDAR? Was it done by air photos, historical? If so, which ones? Because many of these sinkholes we have appear on historic air photos, but don't appear on things now, even LiDAR. They get filled in. Which brings up an important point. So much of what was done with Karst, again, because of what we can see at the land surface, has been based on the location of the sinkholes. And so if you're writing regulation for land use, you would typically do it, as Bob mentioned, distance to a known sinkhole. So let's stop there for a second. If these features are ephemeral, that's a problem. Because we may not know where the locations are, or we may not have good documentation of when it was actually found. So that's a big part of trying to get these attributes nailed down. Who located it, what the method was. The second issue, and this brings the first of the slides I want you to be thinking about, was Sam showed a nice slide, and actually we saw a slide from Wisconsin also of the alfalfa fields. So what we're looking at there were joint patterns revealed in the bedrock by roots in the plants. Okay, so the point being is that we recognize that karst conditions, when we talk about karst, isn't just about what's happening at the surface, we're actually talking about the plumbing. And when we really get down to understanding these databases and their use, we're typically applying the problems that relate to the plumbing. So in other words, the water goes in, but not only in the sinkholes. Sinkholes are the most obvious places, but they're just symptoms of a deeper plumbing that's going on within the bedrock. So being able to map those systems with the features that are now appearing, again, in the GIS environment, like air photos, where we can see joint patterns, that really gets at the actual karst. When we talk about karst, we're talking about the plumbing. We're not just talking about sinkholes. So, the database, again, in Minnesota, has, what, about 14,000 features? I should know that number. Most, again, sinkholes and springs. But as we go forward in this, what we really want to start thinking about is other features that you could also include. Things that we currently are doing in Minnesota but haven't become part of the database. So getting away from just points, but getting to maybe lines. So joint patterns that you guys are doing in Illinois. Getting these into a GIS database is a way to define direction based on the direction and the length of these lines. Another type of line that we added in is a connection between a point and a spring where a dye trace has occurred. There's been a history of dye tracing going on in Minnesota for a long period of time, which is a really nice piece to talk about the plumbing because it gives us a time frame from the sinkhole to the spring. So being able to map out those where that went in, where it came out, that gives to a sort of a line feature, which is something we'd like to build into the database. The last piece I want to get to from a GIS perspective are polygons. So if we're mapping an area where we know that there's karst, for example, we can see in the alfalfa fields where we know there's karst conditions underground but no visible sinkhole, we want to be able to map those areas because these are areas that are critical for land management. We know the water's getting into the ground quickly, we can see it on the photos, but there's no sinkholes there to sort of guide us in our normal way of land use planning, distance to a little sinkhole. So that's kind of the future where we want to go with this database, is to try and incorporate line features and polygon features also into it. And with that, I'm going to stop, because I think we have more discussion about some of these things. But I'm glad Beth can put this together, get a chance to see what's going on in neighboring states. And so,